This is the first part of Chapter 8 on earthquakes and Earth's interior. It's split into two different videos because it's on two different days of the schedule. All right, so earthquakes. Probably one of the more exciting topics that we're covering so far. So it's just the vibration of the Earth produced by a rapid release of energy, and it's typically associated with continental or oceanic plates moving past one another. All right. So it's explained by the plate tectonics theory, and the mechanism for earthquakes was first explained by a scientist named Reed. He basically said that rocks spring back, and this is a phenomenon called elastic rebound. So if you think about taking a spring, all right, if you were to compress a spring, right, so you're using some energy to store energy in that spring. When you release your hand from pushing the spring back in, the spring rebounds in the opposite direction. So this is it's this mechanism that we call spring back. All right, so vibrations, this earthquake, occur as rocks elastically return to the original shape, just think of the idea of like a spring. All right, so here's a picture of a transform fault, and then next to it, the analog if you were to try to break a piece of a tree in half. All right, so as the transform plate is moving one another, that's like bending that tree limb, storing energy in it, and eventually what will happen is the tree limb will break, and that's when the transform fault or boundaries in that transform fault will slip past one another, and that slipping past one another will release energy, causing both sides of the plate to vibrate, and that's essentially what we're calling an earthquake. This is another example of the type of boundary collision of plates that could cause an earthquake, and this is called a megathrust fault, and it's essentially just when a subducting oceanic plate is going underneath the continental plate. All right, seismology. So this is the study of what's called earthquake waves. So there's many types of waves that are produced by earthquakes. These next few slides are going to go through the different types and how we use those waves to determine the location an earthquake originates. All right, so the study of earthquake waves is called seismology, and the instrument that actually records the waves is called a seismograph, or any one single record is called a seismogram. This is an example of a basic seismograph. So you have this rotating drum that's attached to a base plate, which is attached to the bedrock in a region, and then there's this pivot that comes off of a boom that's allowed to rotate and make a recording if the bedrock were to actually move. So this little pin needle that's making etchings in this actual piece of paper that's on the rotating drum, that's only going to move if the ground is moving. So it's going to make a record of the amplitude of the wave and then the time between waves. So that's going to be important, the time between waves. All right, the first type is called the body wave, and we call those P waves because they're pushing and pulling the rock material as the waves travel through the earth. And just right off the bat, too, a wave is simply a way to model energy propagating through matter. So this push and pulling motion is essentially a compression. So if you were to take a slinky and attach to a wall, if you were to pull or push that slinky, you would create an energy wave that travels within the same direction of the material. So you're going to see that there is no up and down motion with the P wave. It's simply a compression wave. And these waves can travel through solids, liquids, or gases. And these are the earthquake waves that have the highest velocity. Another type are called secondary waves. These would give you the shake type of motion, and these only travel through solids. So they're not as powerful as the other waves, and these are a lot slower than P waves. So if you can think of these waves as up and down motioned energy waves, and what it does is as the wave reaches a certain piece of matter, it moves that matter up or down. If you think about the wave in its state in this picture, this part of the rope kind of looks like a little sine wave if you've taken trigonometry before. And now it looks like the sine wave in this picture moved all the way down here. It's not that the matter or the atoms that make up this rope are moving along the direction of the rope. It's just causing the atoms to move up or down. So the motion of the matter in this case is only up or down, where the energy wave is actually moving this direction. So the direction of movement in a secondary wave is always perpendicular to the direction of the energy wave itself. Another type of wave is called a surface wave. This wave is very complex in motion, and it could be in 3 dimensions. It's the slowest of all the velocity different types of waves, but these are the waves that would actually cause the destruction on the surface of the Earth, or these complex surface waves that exist after an earthquake. So how do you locate an earthquake? Well, there's 2 locations that are important. One is called the focus. This is the place within the Earth where the earthquake waves originate. Typically, an earthquake does not originate on the surface. It's going to originate somewhere underground at a location of a transform fault, for example. The epicenter is the point on the surface directly above the focus. And you can easily determine the epicenter simply using the difference in arrival times between P and S waves on a seismogram. All right, because these 2 waves are related to the distance they travel. All right, this is just a picture showing you that the focus is underground while the epicenter is directly above the focus. And you can see that the focus typically always happens along a fault line. All right, so the epicenter, how do you find that? You need, at minimum, 3 stations worth of recording in order to locate the epicenter. So if you think about 3 different stations, right, and assume the waves are moving at a constant speed, if you were to have an earthquake happen, and then station 1, let's say, for example, I'll just say where my the mouse is right here, all right? If this is station 1, and the earthquake happened over here, it's going to take a certain amount of time for the P and S waves to reach that station. So say it takes 10 seconds to reach first station. Well, the station doesn't know from what direction did that originate. It knows that it's only going to be in a circular region representing 10 seconds away from that, from when it first got that recording. All right, so it's 10 seconds away, which means it could be in any direction. The second station, let's say it's over here, does the same thing. It's going to see another circle. So when you have 2 circles being drawn like that, you essentially have 2 possible locations for that wave originating, because the circle is going to have 2 intersecting points. Think of a Venn diagram. Only if you have a third station doing that same circle method will you have 1 intersection point between the 3 circles. There's probably a decent drawing in the book on that. I'm just trying to do it with my mouse pointer here. But just make sure you look in the book and understand how you would locate the epicenter of an earthquake using 3 stations worth of recordings. All right, this is a picture of body and surface wave travel as it goes to different seismographs on the Earth. So you notice the P and S waves travel inside the solid material here. And what's interesting is that, if, let's say, seismograph 1, so at this closest station, you're going to see that the amplitude so it's the up and down motion of the P and sine waves are the greatest here relative to the other seismographs. But what you will notice is that the actual shapes of the seismograph recordings are the same. It's just a little weaker at seismograph 2, and of course weakest at seismograph 3, with the S waves not even arriving yet. All right, so it's very easy to tell if you're closer or farther away from the epicenter based upon the amplitude of the waves on your seismograph. Earthquake intensity. So the intensity of an earthquake is simply a measure of the degree of earthquake shaking at a given location based upon the amount of damage that happens. And we typically measure intensity of an earthquake with something called the modified Mercalli intensity scale. This isn't the scale that's typically announced in the news when an earthquake happens, but this measures the earthquake's intensity due to damage. So this is just an example of an earthquake using that Mercalli scale in 1989. The scale that you're probably more familiar with is the Richter scale, and this is based on just the amplitude, so how up and down a P or S wave gets. So it's based on the amplitude of the largest seismic wave that's recorded. Now each unit of this scale measures roughly about a 32-fold, so 32 times energy increase every time you go up each unit of this scale. So this doesn't estimate the size of very large earthquakes, but it's a good indicator about how damaging an earthquake is going to be, and this was introduced in 1935. All right, here's just a graph showing you, or a table showing you different magnitudes of the Richter scale. So you're going to see that a magnitude 1 is 10 times the amplitude of something that's 0.1, And if you went up to a magnitude 4.0, you're not 4 times more powerful than the 1. You are 10 going to 10,000. So you're 1,000 times more powerful when you have a 4 magnitude earthquake than you do a 1. So just imagine what a 9 or a 9.5 magnitude earthquake on the Richter scale will give you in terms of ground motion. And look at the energy. A magnitude 1 goes from 32 times to 1 million times when you go up to a 4.0. So this is a scale that will tell you how terrible an earthquake is going to be. All right, so in terms of magnitude, the moment magnitude scale so measures very large earthquakes. So this is derived from the amount of displacement that occurs along a fault zone. So here's a magnitude scale, just giving you idea about annual earthquake occurrences. So we have less than 1 a year, which means it doesn't happen every year, something above a 9. And we have about 1 that lies between 8 and 9, and that very rarely occurs in a zone that's populated, but it does happen. There's an example of it happening in 2006 in Sumatra, and then in Mexico City in 1980. And then you have more and more of these earthquakes as you go lower in the scale. And you can see that even New Jersey felt an earthquake of magnitude 3.0 in 2009. So some factors that determine how much structural damage will occur. So obviously its intensity, how long the vibrations happen, the nature of the material upon which the structure is built. So if you're building your house out of cement versus wood, the nature of that material and the design of the structure is going to depend on if it's destroyed or not. And destruction results basically from ground shaking, something called liquefaction, which your book goes into more detail about, landslides and ground subsidence, and then obviously there'll be fires. So there was an earthquake in San Francisco, I believe it was 1906, where the earthquake wasn't that strong, but it caused massive fires, and because they didn't really have a well-developed fire suppression or fire department during that time, a lot of the city ended up burning down because they couldn't control the fires. This is just a picture of some earthquake damage from Alaska in 1964, and this is a nice picture of liquefaction making something called a sand volcano. So the illustration on the bottom shows you how pictorially liquefaction would happen on a small scale. Another thing that you would have to worry about in terms of earthquakes, if the earthquake were happening in a oceanic to oceanic plate convergence and even an oceanic to continental plate convergence, is a tsunami. These are just seismic sea waves. All right, so if an earthquake were to happen, energy would be released on a fault line. If that fault line were underwater, the waves would end up be propagating through water as opposed to just going through a solid piece of rock. All right, so there is a tsunami warning system that would alert certain more susceptible areas, let's say like the islands of Hawaii. But if you were to have a tsunami occur at any of these locations, you would have multiple hours notice before you would have to worry about any propagating waves coming from those areas. Specifically, they list here the Aleutian Islands at the coast of South America and New Guinea over by Australia, simply because these locations are very near fault lines that typically have frequent earthquakes occurring. So, a place like Honolulu, Hawaii would have plenty of time's notice for the waves to propagate that far. And there was actually a recent study that I read about that. If you're more than a couple hundred miles away from a tsunami, you're probably not looking at the type of destruction that you would see as if the earthquake happened at a fault right off the coast of some location. All right, so 95% of energy from earthquakes happens in very few spots on Earth. And it's typically where you have oceanic to oceanic boundaries and oceanic to continental boundaries. So it's just where you have plate boundaries on the Earth where typically 95% of your earthquakes occur. So this is just a picture of that. So you're going to see all of those earthquakes happening along the coast by California. That's right, happening on the San Andreas Fault. And then if you traced out all the different plate boundaries on Earth, you would find most of the earthquakes happening at those locations, noticing that not many happen in northeastern United States very much because there's no plate boundary. Now, how do you predict an earthquake? Well, Bad news is there is no reliable method yet devised for short-range prediction. So if you're looking for a Nobel Prize, there you go. Find a short-range predictor for earthquakes, and then you got it. The long-range forecast is actually it's not bad. The premise is that earthquakes are repetitive. They're going to happen in the same regions on Earth, as we said. So there's in any given region on Earth, there's a probability of an earthquake. So specifically, if you have earthquakes in your region and you haven't had one in a while, chances are you're probably going to have one. Now, that doesn't sound very scientific, but it does tend to work if you look at the history of a specific region and how often earthquakes happen. So if you have a seismic gap, meaning you haven't had an earthquake in a while, it's probably you should probably prepare that you're probably going to have one um, every 2 years, and if you haven't had one in 2 or 3 years, you're probably going to have one soon. There's also something called paleoseismology, where scientists actually study the timing location of prehistoric earthquakes at certain regions, looking at sedimentary rock layers and how they shift. You'd be able to tell, did an earthquake happen this year? So that they could say, all right, well, if this area had an earthquake every 1,000 years, then maybe that area is due for some type of movement. Most of our knowledge of the Earth's interior comes from studying these P and S earthquake waves, believe it or not. So the travel times of P and S waves through the Earth can vary depending on what type of material the waves are passing through. So if we can figure out time differences between P and S waves, and as they travel through different materials, we can actually go back and look at those times and then determine the material in which it passed through. And because S waves only travel through solids, we can pretty much tell wherever S waves are traveling, that's going to have to be solid material. So we can figure out how big, let's say, for example, the Earth's crust is versus the mantle versus the outer and inner cores of the Earth, because certain parts of those materials are liquid. All right, so just some possible paths to end this section of Chapter 8. You can have some earthquake waves going straight paths. You can have some which will actually refract, which means when a wave passes through a material and then it goes into another material, the wave's going to bend in certain directions, and that's called refraction. So you can have some refraction, so we can tell when the wave enters the outer core versus the inner core. We can also have waves reflecting off of the inner and outer core boundaries to tell exactly where those are located. And then we have some waves doing something called total internal reflection. So when you're moving through material like the Earth and you're going into a material like air, sometimes you're only going to have a reflection. So what says double reflection over here, some of the waves actually reflect off of the surface of the Earth, which is the boundary between Earth and air. All right, that's going to end the first half of Chapter 8.